Okay, I thought it might be worth just putting the solution down for question 4 from exercise 20F, just in case you're having some issues, because this is a classic type of using calculus to solve a problem, a max-min type problem. And as you're hopefully aware, what we've been doing is working out, the equation of the gradient of curves, and we've really started to hone in on this area here, haven't we? Where the derivative equals 0, because at those points, we've got something happening. We've got a max or a min, and when we put that into a context of, in this case, we're looking to maximize the volume of something where we've got a fixed surface area. We've got some real use for this stuff. So this is a classic question. Really important you understand how to do it. So this is question 4, I believe. Yeah, question 4 here from exercise 20F. So let's have a look at the solution to it. What I'd like you to do is have a go at doing it yourself. Maybe you get stuck, you need to just go through a stage or two, you pause me again, try and get ahead of the question, and we'll see how we go. So the cuboid is a total surface area of 150. Right, so the surface area of this thing is 150, and a square base of side x. It's all demonstrated, it's all illustrated here in the diagram. Show the height of the cuboid is given by right. Okay, so firstly our surface area, which is 150, but we need to represent that in terms of x's and h's. We've got 6 surfaces here. We've got this square base here, and then there's another one at the other side, so that's x squared and x squared, so that's 2x squared. And now we've got these 4 sort of rectangular faces, which have all got an area of x by h, x by h, x by h, so there's 4 of those, so we've got 4xh. That's our surface area, but we're told that that's equal to 150, so we can make a little equation here. And in fact our first task is to make h the subject of this, and you'll see why in a moment. 4xh equals 150 minus 2x squared. Just isolating h now, h equals 150 minus 2x squared over 4x, which we can improve on by dividing by 2 to get 75 minus x squared over 2x. Right, so that's the first part of the task, writing h in terms of x, because now what we're going to do is we're going to find the volume. We want to maximize the volume. That's the goal, the target, the aim is to maximize volume. Okay, so if we're going to maximize volume, eventually what we're going to need is an expression in terms of V, and then we're going to have to do some calculus on that expression. So volume we know to be x squared times h. There's area of the cross-sectional base times the highest volume of a prism. Now this is no good to us in its current form because we've got 2 variables here. That's no good at all. We want 1. But we've gone to the trouble here of writing h in terms of x. So we're going to now replace h with this expression here in x. So it'll look like x squared, open bracket, 75 minus x squared over 2x. Okay, so let's get to work on this. I can see an x that can go there and there, because that's multiplied out, and that's all I'll do for the minute. I'll now run this x through, so it'll be 75x minus x cubed all over 2. Alright, now I'm not ready to derive this. This is not in differentiable form for me yet. Let's split this fraction up. So 75 over 2x, that's that bit of it. 75x over 2 is the same as 75 over 2x. I want to see what the coefficient is. Make sure you isolate that or separate the coefficient from your x. Always makes differentiating much easier. Do the same over here. I'm not going to write x cubed over 2. I'm going to write a half x cubed. I hope you agree that that's now much easier to differentiate. If I've got x cubed over 2, I can't really see what's going on. I need to see this coefficient. Right, it's the same thing, but it just is in this form. Makes life a lot easier for you. Right, so this is all I've been doing so far is improving my v. Now I'm going to get into it and do dv dx. Dv dx is 75 over 2 minus, the 3 comes down, so it'll be 3 over 2 x squared. That's my dv dx. That's the rate of change of volume with respect to time, with respect to x, sorry. Now when that's equal to 0, I will have, in this case, a maximum, because this is a negative. Look at this. This is a It's a quadratic and it's a negative quadratic, so it'll be doing this. So this is my maximum here. When I solve this equation, I'm finding the x value at this point. So let's go and solve. Multiply through by 2, you get 75 minus 3x squared equals 0. Right, let's get 3x squared on one side equals 75. Now let's divide by 3. Now let's take the square root. Now the square root is plus or minus 5, but excuse me, I'm just going to make a note here that x can't equal minus 5 because x represents a length. Right, so x is 5. What does that mean? That means that I'm going to have a maximum volume in this cuboid when x is 5. So my next job is then to find out what that volume is. Right, so therefore I'm going to come over this side. I'm going to say therefore maximum volume at x equals 5. Therefore maximum volume equals, where's my expression for volume? Before I derived my expression for volume, this one here, I did this for differentiation. This is a nice one to use, so I'll go in there and use that. Maximum volume is 75 times 5 minus 5 cubed, which is 125. Put that over 2. What do we got here? Use your calculators. 75 by 5 is 350. 375 minus 125 is 250 over 2, which equals 125. I think we're in centimeters cubed. So that's my maximum volume, 125 centimeters cubed. Part D, if the maximum side length of the square base of the cuboid is 4 centimeters, what's the maximum volume possible? In that case, you'll just put 4 into what we just put 5 into this expression here. Okay, so just to recap the question, it looks like this. We're given some information about the surface area. We go and use that information to form an equation and make one of the variables in terms of the other, so make one of them the subject, in this case h. Often we're guided that way through the question. We then write the expression for the volume. We replace h with our expression in x so that we've got volume in terms of x only. Our target, let's be really clear on what our target is to maximize volume. So I need to get an expression for volume and then dvdx it, make it equal to 0 and solve it. Ding, ding, ding. Remember, you can use your calculator for all this stuff. X equals 5 is my solution. Put that back into my volume expression to find out my maximum volume. Okay, hopefully that helped. I'm going to put another YouTube lesson up for the next area that we're looking at. Still in rates of change, still in calculus, still in differentiation. But we need to keep this show moving. Okay, see you soon.